Hello world, my name is Nikita Black, and I'm happy to see you on my channel. Today we will continue to develop our application. We will touch different things, such as pipeline barriers, image layouts, semaphores, synchronization in general, and we will talk how operating system presents images on the screen. In the end, we will have more than just a black window. This time we will have a green window. I told this many times, and probably I will tell more, that Vulkan is a very, very explicit API. Just to have this simple green color, it requires hundreds of lines of codes, many hours of programming, as you see. And what's more important, it requires a deep understanding of what we are doing. As you can see, I'm already in my favorite Vulkan hat. That means that we are ready to dive in. See you in the code editor. As usual, I will start with creating a new branch for this episode and also with corrections to my previous video. And there is something to do. I remember in some function I used this construction and accidentally I put here the wrong data type. So instead of application info, let's say I put something else. In this case, the S type will be wrong. This will compile, but it will bring us troubles during runtime. It can crash and maybe it will not crash, who knows. So that's definitely wrong. To not typing the S type by myself, I used the helper, but there is a better way to do this. So I'm using the helper not to its full power. This helper allows us to do the following. We can use this init struct helper and remove this S-type complete. Let's see how this works. If you go to the definition of the helper, we can see this cast operator. Every time when we assign struct helper to some type, like here, the cast operator is called and the cast operator calls init struct. And this init struct calls S-type and assigns the optional pNext pointer. That's all basically we need to do. We need to remove the manual explicit call to S-type and pNext and just provide this information, and in the places where they need pNext, we can specify it in constructor or just leave it as it was. I will provide it here. This gives us some guarantees about mistyping and also saves a couple of lines of code. Let me quickly fix this and then we will continue. Now our application became a little bit better. All we need to do is just assign this helper to a structure. The cast operator will call all the necessary magic. It will work. And here an example how to provide some pNext pointer parameters to the structure. So it's just passing the pointer to this helper. The only place I have to do this separately is here in create device function, simply because my getChain returns const pointer. But init struct helper expects just a normal pointer. I could change here the pointer type, but I would prefer not to do this. I tried to compile it at work, I tried to run it, everything works. Now let's discuss what we will do next. And today I want to do a little bit of rendering, not the rendering you maybe imagine, but just the clearing operation. So instead of seeing the black screen like here, I would like to have something pink, for example, or my favorite green color. Also, if you start to resize it currently, we see that the window shows us some garbage. It just shows us some memory which operating system just assigns to this window. We created Swapchain last time, but we never used this, so this is not the Swapchain, or maybe it is, I don't know. And the idea is to get the Swapchain, clear it to user-specified color, and that's it for today. I think that's already will be enough of topics we have to cover, and there will be a couple of very important concepts in this video. And today we'll start with a simple version, because my idea is to have an off-screen rendering to a render target buffer, and then to use this render target to copy the contents to the Swapchain and present the Swapchain on the screen. I don't want to create a render buffer yet, because it's too complex. Instead, we will do this temporary solution where I will present the Swapchain, but again it will cover a couple of very important concepts. That's basically the plan. Let's start by creating some stub functions, and later let's figure out how we can proceed. Here's the plan how I will do this. In addition to start frame function, I declared and defined the end frame function, and in my main code I call the start frame to begin the frame, to initialize everything we will need, and end frame indicating that the frame is finished, and in between start and end we can draw something. And here in this to-do list we can see what we need to do. First we need to get the Swapchain index, then we need to clear the image, then we need to submit, to present. We don't know yet what all these list points mean, but we will figure that out as we go. So let's start with Swapchain index. What is it and why do we need this? And the Swapchain index is pretty straightforward. When we want to present something on the screen in a window, as you remember, we can do this through Swapchain images. So the images which operating system allocated for us set all necessary properties. And now we ask operating system to tell us what is the next Swapchain image you're going to present, so I can render into this. Vulkan has a special function to get the index. So instead of image or image view, it gives us an index. As you remember, when we created the Swapchain, we specified the minimum number of images, and Vulkan created correct number of images. And now we ask the operating system, please give me the image index, and I will try to render into this image index. Again, here we store these images, and we simply will get the index in this vector of images, which we can use later. As usual, I will create a function where I will call this Swapchain index Vulkan function. Let's see. Here, how we get this index. First, we need to call Vulkan function, acquire next image. There is not strictly necessary to use the function number 2, just this one would work as well, but as mentioned before, I would like to have the latest versions in my application. This function takes the result and the info, which is the most interesting piece of code here. In info, we provide the Swapchain. We also provide timeout. It just tells us how long should we wait until operating system can give us the number, this index. Here we are saying we're basically waiting indefinitely. Also, here we use device mask. By the way, it should be 1. The device mask is a special thing. It's used when we have multiple GPUs or we have a GPU subdivided into multiple parts, which we will not do in application. That's why it's 1 pointing to 1 and only 1 GPU. And these two fields are unknown. What are semaphore and the fence? First, let's look at the documentation. Here it tells we need semaphore on null, fence on null, some other stuff, and here we need to look at the valid usage. Here it tells us that both semaphore and fence can't be null, so one of these can be null but not both. By the way, it also tells the device mask must not be 0. Let's quickly discuss what are these semaphore and fence. Semaphore and fence are synchronization primitives in Vulkan. Semaphore used to synchronize work inside the GPU, to synchronize work between queues, for example. The main idea that on the CPU we never know the result of the semaphore, so everything happens on GPU. GPU writes and GPU reads. On the other side, fence is what we are using when we want to synchronize the CPU and the GPU. For example, we submitted some work and we want to know on the CPU when this work is finished, and we use fence for this. In our application, we will use semaphore because using a fence would mean that while we are waiting for GPU work to finish, CPU does nothing, and actually GPU also does nothing after we finished to wait. That's not good. Though the delay is not that critical, it's not milliseconds or something, but still. So we always want that the GPU is fully saturated and the CPU as well. We always want to have these two devices run in parallel and never waiting one another. Of course, we at some point have to wait, but we want to minimize this. That's why we will use fences in some special place, but not here. We want to stay on the GPU when we're dealing with Swapchain image. Summarize. Semaphores when we want to synchronize the GPU work, potentially between multiple queues or just GPU work, and fence when we want to synchronize CPU and GPU. Okay, now when we know this can be null, and the semaphore, we have to create one. So let's create a function which will give us a semaphore. Okay, let's look what we done. First, the semaphore. So here I called it image available semaphore. We will figure out in a moment why this name here. And also I put here a lot of exclamation marks. Just a spoiler, this thing currently will not work. We will see shortly why. My idea here on this channel is to show what could happen if we misuse Vulkan, to show some wrong usage of this, to show errors. That's, I believe, how people learn better, because there are always questions, at least for me. I always have questions like, what will happen if you do this or if you do that? And here I'm trying to follow my process of thinking. What happens if you do it like this? Let's keep it for now. So this is how we create a semaphore. We don't use any fancy stuff here, just semaphore info, and just ask for a Vulkan function to create it. Nothing special here. And we provide the semaphore to Swapchain. Now, what exactly is this semaphore? As the name suggests, it tells us when this image actually will be ready. Let's look again at the specification. Specification tells us that the semaphore defines semaphore signal operation. The keyword here is a signal. And again, this function does not return image or image view, it returns an index. It's kind of operating system looks into the future and will tell the next image which I will present on the screen will be image under index 3, for example. But when it's ready, actually, we don't know. And for this, we are using this semaphore. So what happens? We provide the semaphore to this function. It returns us an index, and later it will signal the semaphore telling that, okay, I'm finished with everything and image now is ready to be used. And only then this image is ready to be used, we can render into this. If you try to do it before, it's undefined behavior. So that's why we have to somehow synchronize the GPU work, and for this we are using a semaphore. We can do this with a fence, so we can wait on a CPU, then image is available, but in this case there will be a signal sent from GPU to a CPU via PCI Express, for example, which takes time, and during this time both GPU and CPU are idle. We don't want to do this, and after we receive this information on the CPU, we can proceed and tell next instruction to the GPU what to do. So again, we don't want to use this, we want to be very fast, that's why we are using semaphore. That's basically it. This semaphore tells us that we can use the image under image index, and that's it. And one thing important is that the success for this function is not only success itself, but also other success codes. For example, again, the holy specification, it tells us that return codes for success, it's success itself, suboptimal, not ready, or timeout. So timeout, we using the maximum number, so that means we will never get this timeout. Success is good. Not ready, I'm not using this actually because I never saw this, but yeah, maybe we can add this. We will see how it will behave. And another code which is not used here is out of date. This could happen. I saw this on my machine, for example, when we resize, the Swapchain can be out of date as well. So that's why I'm not treating this as error, but instead I just raise the flag. Should we rebuild Swapchain or not? And inside the graphics manager, inside the start frame function, when I get the result of this function, I check should we rebuild it or not. Actually, we can use the Swapchain if it's not optimal. They call it suboptimal. In any case, I will just rebuild it. We handle resize here, so strictly speaking, we should never hit this function, but I will put a breakpoint here. We will try to resize heavily to see what will happen. Now, if I compile, it compiles, but when I run, this will not work. Let's see what happens. So it crashes immediately, and here, again, the layers, they are very important for development, and they tells us what's going on. The first line tells that the semaphore must not be currently signaled. And again, if you open the specification, we see this valid usage. It tells us that the semaphore, if it's not null handle, must be unsignaled. When we create the semaphore, it's in unsignaled state. It's only signaled, then we call this function. As you remember, this is a signal semaphore. That means if you put a breakpoint here and run with the debugger, the first time we hit this place, it will not crash. For some reason on my machine, when I have my validation layers running with Vulkan configurator, I always have to wait a couple of seconds because starting of application is very slow. It happens in create instance function, so it just takes a long time, on Ubuntu 20 at least. So we hit a breakpoint for the first time, I continue here, I press F5 and we do not see any layers. But now if I make a step forward, that appears. This is because this semaphore, it was signaled, but we never actually cleared this. And you may think, okay, we can clear the semaphore before calling this function, but we can't do this. The semaphore is a thing which lives inside the GPU, and there is simply no Vulkan function, something like Vulkan clear semaphore stuff. Instead, we have to provide this semaphore to some other function, and if this function defines the semaphore wait operation, remember that what we defined here is a signal operation. There is some other stuff like a wait operation, and during this wait operation, the signal will be reset. The semaphore will become a signal. And in our case, this function will be submit function. So when we submit, we need to wait for this image to be available. The submit means that we prepare some amount of work for the GPU, rendering work, for example, and we telling the GPU during the submit to do this work. And this submit will wait for this semaphore, and then this image is available. The GPU will start to work to render into this image, making at the same time this semaphore is on signal. So the next step for us is to create this submit function. Okay, so this function is somewhat complicated and I put a lot of question marks here. Let's try to understand what's going on. This is the final function which we want to call, the Vulkan function, and it requires a bunch of parameters. So the first parameter it requires is a queue. We already have a queue, and in our application we have exactly one queue. But as I recall, it's possible to have multiple queues, and it's possible to submit asynchronous work, meaning the work will be executed at the same time if you have multiple queues. We can have, for example, a transfer queue for copying data and the graphics queue, and these two queues can run in parallel. Modern GPUs usually have special dedicated hardware, and they can execute multiple things at the same time. So we have a queue, we have to provide it here. Next is the number of submit infos, we have only one, and the later parameter is a fence. We will need this in the future, small spoiler, but for now we can leave it as null. Theoretically, it should work, but I will come later to this. The submit info struct requires a lot of parameters to be filled. The flag 0 we will not use. The wait semaphores. This is what I was talking before. This is the semaphore which will be fired when we are ready to start to do work submitted with this function. In our case, we have image available semaphore. As you remember, this semaphore indicates that the image is ready to be rendered to, and the submit function will wait for this semaphore. It will wait, then the semaphore is signal. After it is signal, the GPU work can start to execute. Next is command buffer infos. We submit commands not directly one by one, but we usually collect a batch of commands into so-called command buffer, and this is how everything works in Vulkan. We don't submit usually a single operation, we collect many things to execute an order and submit it via command buffer. We do not have it yet, so the next logical thing would be to create the command buffer, and we will see it later how it's done. Signal semaphore is similar to wait semaphore, but as the name suggests, it doesn't wait for something, but instead it signals. When some operation reaches a certain stage in the pipeline, the semaphore will be signaled and we can do something with it. We will use this in the future because we need to, but for now, I think we can leave it. We will start with this and we will see how it behaves. Next, the image available semaphore, the wait semaphore for our queue, we provide as another structure, semaphore submit info. Here we provide the semaphore itself. This value is a special thing for special semaphore. There are two kinds of semaphores in Vulkan: normal, which we are using, and the so-called timeline semaphore. The difference is the normal semaphore can have just two states, signaled and unsignaled, while the timeline semaphore has special value, integer number, and it can have multiple values during its lifetime. Again, we will not use this in our application. They just make it a 0. The API will ignore it because we are using normal semaphore. Device index is, again, if you're using multiple devices, this is index in this device group. We don't use it, hence it's 0. Next is the stage mask. Stage masks and also access masks is somewhat confusing thing. In Vulkan, it relates to synchronization. But for now, we can think about this the following way. There are multiple stages in the pipeline. For example, vertex stage, fragment stage, compute stage, and there are some other sub-stages between. There is a stage where the GPU retrieves the indexes if you are using index buffer. There is a stage for early fragment tests and late fragment tests. There are a lot of different stages. We are using the image, and this is a Swapchain image, and we are going to render into this image. The logical thing would be is to wait when this image is available in some dedicated stage for this. For example, we can put here some random value. For example, we can put here vertex shader stage. It will work, but in this case, the queue submit operation, when it hits a vertex very early stage in the pipeline, it will wait until the image will be available. It can take some time, and the important thing, the GPU will do nothing, it will stay idle. But for example, we don't need the image in this early stage, right? Because we are rendering normally in the later stage, the fragment stage. So we can put here another stage, more later stage in the pipeline, meaning that the operations which are earlier, they can execute, and then some command will hit the stage which is specified here. So again, this thing is correct, but it's not optimal. We can do better. In our case, we will use color attachment output stage. And let's look at the documentation. It says that this stage specifies the stage of the pipeline where the final color values are output from the pipeline, and it includes load and store operation for color images. This is exactly what we need. Again, we are waiting for image to render, and we are going to write. In other words, we are going to store into this image. So that's why we want pipeline to stall here if the image is not available, and wait in this stage but not in earlier stage. Okay, with that said, let me add the missing info here and also create the command buffer, and I will explain as soon as I finish. Okay, so I added the submit function, but again I have to put here the question marks because we don't know yet what to pass here. Let's start with the queue. Let's go back and see how we worked with queue before. We didn't create any queues, but we got the graphics queue family, where we just took a first queue which supports graphics and present operations, but that's just the family, and we never created the queue. And when we created the device, we also filled this queue create info, and we specified the family and the number of queues we want to use with this device. In our case, we use queue count, as you remember, and queue count is only 1. So we will work with a single queue family. When we created the device, Vulkan also create the queues, and all we need to do is to get these queues out of devices. And we didn't do it up until now, so let's do it. Okay, so getting Q family is pretty straightforward. All we need to do is to take our device and take Q family index and say which Q we want to take from this family index. Of course, the Q index should not be greater than we specified when we created the device, the same for family index. And as you can see, this function returns void, meaning it can't fail. Theoretically, I don't know actually what happens when we provide here the wrong indexes. Probably validation layers will complain, but yeah, I will not check this. And we call this function immediately after we created the device. For this, I created a small struct with family index and the Q itself. We need this very often, so usually these things come together, the Q and the index. That's why I created the small wrapper to always have everything at the same time in the same place. And we just call getQ as soon as we have a device. And later I pass this Q to our submit function. Next is the command buffer. The command buffer is a very important thing. In Vulkan, as mentioned, this is the only way to tell GPU what to do. And command buffer is not that complicated as synchronization, for example, but as everything in Vulkan, it requires multiple steps to do it. Command buffers can be used in multiple different ways. For example, in multi-threaded applications, we can have multiple command buffers and we can record commands to this buffer in parallel. And later, these multiple command buffers we submit to one main command buffer. There's also special secondary command buffers and primary command buffers. Our application will stay simple. We will not use multi-threading. We will not use secondary command buffers. All we need to do is just to create a single command buffer top frame. The idea is to have this special primary command buffer, which will hold all commands for the given frame, which we submit to our queue. Yeah, sounds easy. The question is, where do we get this command buffer? Yes, and we get it with a command buffer pool, a special memory, which we pre-allocate upfront. And actually, this makes this operation getting command buffer is pretty performant, and this is quite common operation, so it's designed to be very fast. Yeah, the first thing we need to do is to create a command pool and to allocate a command buffer from this pool. Let's start with the pool. Excellent. It was a little bit of work, but everything is pretty straightforward. I started with creating a command pool. Here I'm creating an info where I specify the family index. When we create a command buffer, Vulkan have to know upfront which command buffer goes into which queue. Here we need to say this command pool, and all command buffers from this pool will work with this queue family index. Also, I set this flag for command pool. Let's look at the documentation. What does it says? And it says that this transient bit specifies that the command buffers allocated from the pool will be short-lived, meaning that they will be reset or freed in a relatively short timeline. This flag may be used by the implementation to control memory allocation for the pool. So it's just a recommendation, a hint to a driver, to Vulkan, to place this short-lived command buffer in special place, special memory, making it a little bit faster. And yes, our command buffers will be short-lived. We will allocate a command buffer in the beginning of the frame, we'll fill it with comments, submit it, and after this, we don't need this. And then I call create command pool command, usual stuff, nothing special here. And I store this in this new variable, command pool, and notice this exclamation marks again. We have to modify this in the future, but for now, let's just keep it like this to see what will happen. Okay, after we created the command pool, we need to allocate a command buffer. For this, I created another function, allocate command buffer. Here, I create an info where I specify the command pool from which we want to allocate a command buffer, the number of command buffers. We can allocate many, and actually that's the recommended way to do this. In our case, we will use one for a frame, so that's fine. And also I specifying that this is the primary command buffer. We will use primary because we work in a single frame, so usually then you have secondary, you create many command buffers, then you merge everything into one. We don't touch this. And then I call allocate command buffers. That's it. So we have a command buffer, but that's not the complete story. You can't just use the command buffer as it is. The command buffer has a lifetime. Documentation actually has a pretty good explanation. Just think that then you allocated the command buffer, you're not ready to use it because you first need to put it in special state, basically marking it as ready to accept commands. And after you finish, you need to mark it as finished. So, in the beginning, before recording anything to a command buffer, we need to begin this. And this is how we do it. Here I specify that we will use command buffer only once. It's possible to reuse it multiple times. Again, we will do this. There are other flags. Also, I will not touch this, so that's fine. This inheritance info, I don't remember exactly. I'm too lazy to look at the documentation. I think this is related to the secondary command buffers. Yeah, and we just call this command and hope that everything goes good. And after this, we have our command buffer and we specify it to submit. As you can see, everything compiles, everything is fine, but I guarantee you it will not work. I have my validation layers enabled, so let's start it and let's see what happens. And we see a lot of warnings and errors. Something is clearly wrong. Let's start from the top. The first error tells us that in order to use VKQSubmit2, we need synchronization to feature, and it's not enabled. Okay, let's remember we need to enable the feature. The second one tells that the command buffer is in incorrect state. This is what I just told. Before submitting, we have to mark this command buffer as finished. Let's quickly fix these two errors and continue later. Okay, the first fix was pretty easy. We already had everything in our features. Before I commented out this line, and I said that we add this as soon as we find why we need this, and this is exactly the place. So we need it because we are using the function which requires feature to be enabled. And this is the part of Vulkan 1.3 features that's done. And to end command buffer, we just call this Vulkan end command buffer function, and that's it. So everything what should go into command buffer should happen between these two lines, between begin and end command buffer. Let's compile it again, and let's try to run it. Okay, again, we see another set of errors. Let's look closely to what this error says. So it says, if semaphore is not null, and in our case we use an image available semaphore, it's not null, it must not have any uncompleted signal or wait operations pending. Basically, what it means is when we are trying to acquire the image here in get Swapchain image index, it complains that something wrong with our semaphore. The interesting thing, it happens not on the first run. So if I start with debugger, let's wait a little bit. We already saw this. So this happens on the second iteration. Here I step over and we do not see any errors. I continue. So this is the frame number 2. I step over and yeah, again, the validation layer fires an error. And the question may be why? So we are using the semaphore here and then we submit operations and just the submit should wait, right? Because it has this wait semaphore info, which should wait, and automatically after it waited, it should put the semaphore to unsignaled state. So what's going on? Why does it work? And this is one of the main concepts in Vulkan, the so-called frames in flight. I think it's better to explain this drawing some pictures. Let me first draw something simple and I will explain what actually happens. Here's my primitive programming card. With it, I will try to explain what I want to say. We have a timeline, just a time, which goes from left to right. And in this timeline, we have two devices, two entities, CPU and GPU. This is two completely different processors. They coexist on the same laptop, computer, but they're different. So what happens when we submit work to the GPU? On CPU, we have a command buffer. We fill it with commands and we send it to GPU. When we send it to GPU, work doesn't start automatically. First, this have to go through driver, then it has to go through PCI Express, for example, and then inside the GPU, this queue have to start to execute. It will take some time. That's why they are not aligned, these boxes. This work will start some time later. But on the CPU, at the same time, if we will look at the code in our main function, I don't know why it shows me red squiggles. Here we just have the while loop, which doesn't wait for anything. It just runs. That means that when we start frame, we end frame. We submitted our work, we immediately start the next frame. And in this next frame, in the start function, as you remember, we call this acquire Swapchain image index, which uses the same semaphore which we used before. But the thing is, we started the next frame before the GPU even started to work on the previous frame. That's the problem. We have undefined behavior. We are trying to access the resource, which is in use by another, let's call it thread, but it's another process. The simple solution to this is to just wait, then this frame is finished, and then we can start to do the next frame. Let me update this image. For example, like this. After we finished the first frame and we submitted the work, we can set a special instruction, special command, basically saying, wait until the GPU is done with this work. In this case, the CPU will be idle this period, and after the function returns, meaning the work finished, we can start with the next frame. Let's see this in action. That's it. Just this single call is enough. So it says wait until this queue completely finish what was submitted to it. There is another command device wait idle. This relates to device, basically all queues, but for us it will be equivalent. Let's compile it and let's try to run this. This error is special because we are trying to acquire the next image while we didn't even present it, single one. I thought we can just submit operations without presenting, but that's not the case. Since we acquired the image, we have to present it, otherwise we get this errors. Okay, not a problem. Let's create the present function and see what happens next. Okay, we made another step. Let's look what I have added. I added the present function, which is responsible for presenting on the screen, and this is how it's implemented. Again, another structure. Let's look at the last field. Swapchain count as 1 because we are using only one swapchain. The image index which we obtained for this frame. This result is used when we use multiple swapchain. We can have many if our hardware supports that. And if you want to get the result of this function for each swapchain separately, we need this one. Since we don't use multiple swapchain, we can pass a null pointer here. And we call this function here. It returns some results. If we look at the documentation, it says that the success for this function is either VK success or VK suboptimal. We handle suboptimal in another place when we are requesting index, so here I do not handle this anyhow. Then the most interesting part is this another semaphore. In submit function we had image available semaphore. As you remember, we passed the semaphore as a waiting semaphore, so GPU will not start to use this swapchain image in this stage until this semaphore is not signaled. And when we need to present an image on the screen, we don't want to present it before it's ready, right? In this case, we need some mechanism to tell operating system to not to present an image until the rendering is completely done. And for this, we are using the signal semaphore. I call this rendering finished semaphore, and it basically does what it tells. It will be signaled when the rendering is done. Basically, it says that similar to here, we are waiting in this stage for this image to be ready. And similarly, when we reach to the stage, when the image is ready, its output is ready, so all the store operations are finished, we set this semaphore signal. I create the semaphore here together with this one. And also I added some exclamation marks, meaning something awaits us regarding this semaphore. But yeah, the idea. this signal rendered finished is used here as a signal semaphore, and at the same time we are using this in the present operation, so the presenting will not start until the rendering is not finished. We are building a small pipeline. Request an image, waiting until image is ready, and then waiting until image is ready to be presented. That's it. Also, I created this variable just to store the Swapchain image for the current frame. I initialize it here in the start frame and use it here because, yeah, that's what is necessary for presenting. And now let's compile, and now let's try to run it. And again, we are seeing a lot of errors. Validation layers tells us something wrong with the Swapchain image. Let's try to figure out what exactly is wrong. The explanation is actually very good here. It tells us that for presenting, the image should be in present layout, but the layout is undefined. Now the question, what are these layouts? And this layout is very GPU specific thing. To explain it in a couple of sentences, I would say that a GPU uses different memory layouts for different operations. For example, when you write to an image, GPU can use special layout which is most suitable for writing operation. But for example, when you read from an image, it can be different layout. These layouts exist only for images. Different GPU operations expect that image stored in the specific format. A GPU can't track the state of an image, so we have to do this explicitly. We as programmers have to tell Vulkan, this image was in this layout, and now I want this image to transition to another layout. That's it. Basically what we need to do is to move our Swapchain image to a specific format, and we normally do this before we draw, because to draw an image have to be in some draw layout, and then we want to present, we will transition it the second time. Here, before clearing, clear is basically storing the data into the image, we have to move our image to store layout, and after we finished with clearing, meaning that we are ready to present, we need to move it to present layout. And to move an image to another layout, we are using so-called pipeline barriers. And as usual, it requires a couple of info structs to be filled, and since these structs are pretty lengthy, I will create another function just to save a couple of lines here on the screen. As always, first I write some code and then I explain how it works. Okay, I added another function, and yeah, it's quite verbose. You can see we need to be very explicit with Vulkan. So here, currently, I have only image barrier, but later this utils will grow. I will add a buffer barrier as well. That's why it goes to utils folder, because we will need this function as a general framework. We will use it as a shortcut to create barriers. So what we need here? First, we need to know the sub-resource range for the image. We already discussed this before. That basically tells which part of the image we want to modify. Since we are using only simple images, no MIP mapping, no layers, arrays, we are using the first level of the only level of the MIP map, the same for layer array. The aspect will be color aspect. There are different aspects. There is also a depth, stencil, but since we are drawing into this image, we will use color aspect. If in the future we will use a depth buffering, it will be different aspect. That's why this goes as a separate parameter. Next thing is the barrier itself, the description of the barrier. Here it requires the source stage, source access. Basically, the source and destination means some resource, where it existed and which kind of operation was on this resource in this stage before the barrier, and what is expected to be the next stage and the next operation. Also the layout. Yes, we need to specify old and new layout. That's what I was told before. Vulkan and GPU can't track the layout, so we need to tell explicitly the old and the new one. I know there is a new extension for Vulkan which should allow in the future to completely ignore this layout transition. This will happen automatically, but for now we have to be explicit. Next, fields unnecessary if you are using multiple queues and we want to submit our operation for different queues, which we don't do. So that's why we completely ignore these fields. And then image itself, together with the sub-resource range for this image. And the last thing is dependency itself. There is only one function for barrier. It works for both buffers and images. And here we tell that we are using this barrier with our image. So we ignore all fields which are not relevant for us and just set these parameters for our image. And then we just add this command to our command buffer. You can see this doesn't happen immediately when you call this. We just here write our attention in the future. And this command buffer will have some operation in some order as it grows. And these operations should start according to order as we wrote it to the buffer. And now how we are using this transition in our code. Before rendering to it, before clearing or drawing to something, we take our newly created command buffer, we take the swap image. In this case, only the index is not necessary because it expects the image. And since we have all images and we know the index, we can get this. Then we are using the color part of the image. Next, the source, stage and access. This presenting is a very specific operation because presenting is not the part of the Vulkan itself. Presenting is part of operating system if you wish. That means that these flags basically tell we have nothing to do with Vulkan. This image was touched by some other entity, operating system, but here how it should be done. Then we tell that the destination stage would be color attachment. We already saw this, that this is stage where write to an image happens, or load of an image. And also we are saying what kind of access to this image happens in this stage. And we are going to write it, because we are going to clear it. If we would read from this image, then we have to also add read bit here. And next, the most important stuff, what was our layer error about, is the layout. Here we tell that the old layout undefined. In Vulkan, that means that Vulkan doesn't care what was before, what was the previous layout for this resource, for this image. And that means it can do anything with the memory, it can completely overwrite it or modify it somehow, so it simply means it doesn't preserve any information. And the new layout is optimal for rendering into this. Optimal means very GPU specific. It would be different for different GPUs. How GPUs store images in their memory, it's opaque for us, so we don't know. But the thing is, if you try to read the memory of this image while it's in an optimal layout, you will probably get not a garbage, but just some random numbers. You need to know how everything is organized in memory in order to understand. Since the drivers know, it would be easy for the driver. And next we do some rendering, which is empty for now, and then before sending the image for presenting, we need to move it to layout, as layers told us. Here we use the same operation, the same comment buffer, the same Swapchain image, the color. Now the source stage. You see they are flipped. Before it was destination stage, then some rendering happened, and now it became the source stage, because we want the barrier to happen exactly before reading. So we want to split operations. Something happens before, something happens after the barrier. In this case, for this second barrier, the previous stage was the writing stage, the access was right, and the next stage, that basically what was before. Since that's not part of the Vulkan, but part of operating system, we are just telling that this image is not touched by any Vulkan part. And for layout, the old layout is color attachment optimal, and the new layout is present layout. This should do the trick. Now let's compile it, and now let's try to run it. As we can see, no errors at all. This is very good. Good, it works, but there is still a small or not small bug here, and this happens then I start to aggressively resize the window. It tells us failed to present. Now if I put a breakpoint here and run with the debugger and start to do the same aggressive resizing, hopefully we can see what's going on. So I need to do this several times. Yes, this condition is false, and it tells us that the call to present returns out of date result. And that's quite interesting, because in getSwapchain we handle this case, and we are rebuilding our Swapchain how this could even happen. And the problem is because we can resize in between this and this function. For example, in this case, in this place, everything is okay. We didn't resize, but since we are doing this aggressively and there is no any pattern to this, we can predict the actual resize can happen between this function and this function, and at the time when we reach the present, we resize the window. Operating system already marked the current Swapchain as out of date, and we have this error. How I handle this? I simply add this check here, which means that after this call, if Swapchain is wrong, since this is our last call to the Vulkan, and we don't do anything with Swapchain, we just ignore this, and next time we start our frame, we will handle the same case here, and we will rebuild our Swapchain. Now if I compile it, and if I run again, hopefully it will not happen. I can do it for a while, and everything seems okay. Except that we get another message that tells us something about image index, about the semaphore. And this time, this is because when we try to get an image from a Swapchain, and if it needs to be rebuilt, we're basically rebuilding the Swapchain, but we still use the old index, which can be wrong. I usually have here a loop, which I call multiple times, until I receive the final result, which is good for me. Let me fix this part of code and explain how this works. Here my approach to this problem. Every start frame, I try to get Swapchain image index, and if I detect that it should be rebuilt, the Swapchain have to be rebuilt, I call the resize function, which rebuilds everything, and the next iteration, again I try to get the index. Hopefully everything will be okay this time and I don't need to rebuild this. If for some reason this function also returns me that I need to rebuild the Swapchain, I do this one more time and I set the maximum counter up to 10. That means that if something weird really happened and Vulkan continuously reports me that I need to rebuild the Swapchain, that's definitely wrong. And in this case I just fire an exception because we can't do anything with it. But in my practice, I never saw this happens more than once. Now, if I try to do this, I can do this indefinitely long time and nothing bad happens. So this aggressive resizing is handled correctly. Now I closed the window and you see another warnings here, but in this case they just tell me that I didn't destroy the objects which I created, and this is because for this part we created a lot of new stuff. We created Semaphore, command pool, but we actually never destroyed them. For example, this command buffer we allocated, but it was not destroyed. And to destroy this we need to destroy the command pool. Yes, this works. I will keep this for later, because we will touch this anyway. Now it's time to actually see different color, not just the black one, but as you remember, my favorite green. How this done in Vulkan? In Vulkan we can't just render to something as usual. We need to do multiple steps. In the first version, Vulkan 1.0, it was very complicated and difficult to understand the process. First of all, in order to draw anything, we have to have a so-called render pass. There could be many render passes, there should be at least one. And each render pass was consisting of multiple subpasses. In order to draw something, you need to have at least one subpass. And all these render passes and subpasses, they have to be managed and used in different other structures like pipelines. With time, people realized that's too complicated because this render passes thing mostly useful for mobile GPUs. There they use so-called tiled GPU architecture, which is not our case, and I think it's not the case for many applications. With time, people introduced another approach to this problem. Now it's possible to get rid of render passes and just use so-called dynamic rendering. In one of the Vulkan versions, I don't remember 1.2 or 1.3, we will figure out this soon. They introduced dynamic rendering as a part of Vulkan, which doesn't require to use render passes and which is much simpler. And this is what we will use in this application. Yeah, basically we will do dynamic rendering to clear our screen. Let me write some code now. Amazing, we did this. After so many hours, we finally have the window with clear color. Yeah, that's Vulkan. Before launching the application, let's see what exactly I did. So I added this begin compose rendering function. I give it a name because the idea in the future is to use a render target, and then as a final step to take our render target and to draw it to a Swapchain image, and also to apply UI rendering on top of this, basically composing everything we have. Well, that's why it has the name compose in it. Let's look inside. I moved the barrier. I removed from here and just copy pasted it here to prepare our Swapchain image for writing. Here I specify the clear color, green, my favorite. The clear color can have multiple types. We can specify it via float or int or uint. Clear value, here we assign the color. It also has depth stencil. We don't use it right now, that's why it's empty. And here we have attachment info. Attachment info is basically what we want to attach to our pipeline to render into. Basically, attachment is a render target in Vulkan terms. Here we are operating with image views. This time it's not image, but image view. You remember, we can have an image which consists of multiple MIP maps, for example, or multiple layers. So we can select one view, for example, one MIP map, and just draw into this. Yeah, but our Swapchain image is simple, so we have a single view. This is the image layout. For the specified here, we need to repeat this because Vulkan needs to know. This resolve mode, resolve image, and image layout, these things are about multi-sampling. We don't use it, that's why everything is some default values. This load and store operation, it means what should happen with the image. Then the data is loaded by GPU, by Vulkan. Here we specify that we want to clear, because we want to use this clear color. There are other options, for example, option don't care. That means there is nothing will be with memory. There are some cases where we want to use this, and we will see. But in our case, we want this thing to be cleared to our color, and the store operation, after the stage of the pipeline is finished, we want this value to be preserved. That means that this memory will be flashed to the main video memory, and we can see it. Here we can ignore this as well, don't care. This also has some specific usages. For example, it's very important to use this on mobile tiled architecture GPUs. But here we need to know that we want to clear, then it's first introduced this image, and we want to keep this cleared value or whatever we rendered, and the clear value. Also, we need to specify the size, the render area. We are using the complete extent which we got when we sizing the window. We don't use any flags. The layer count, we can have an image with multiple layers, probably. I actually don't know, I never used this, but yeah, that name suggests that we can use multiple layers. The view mask, it's possible to have multi-view rendering. You won't use it, that's why it's empty. Our attachment, and again, we don't use neither depth nor stencil, that's why it's empty. And finally, we call this begin rendering, which sets the instruction to a command buffer. And that's it. I have my validation layers running. We will see this when we close the application. It will complain some destroyed objects. It compiles fine. Now we can try to run it. Excellent. The beautiful green color. We can resize. I don't see any warnings, any errors. Very good. That's a major step in our application. Yeah, I closed the application, and this is what I mentioned just now. It complains that many objects were not destroyed properly. Okay, that's it for today. I'm leaving the application in a slightly broken state because of all these numerous validation layer warnings. We will start next video with fixing them. Now I will push the changes, so if you follow me, you can just take this branch and look what we have done. And see you in the next video. Take care.